Well, you can get evidence from places other than what we've seen before. We can get it from trace elements of metals, get it from paint, and also soil. So let's see a little bit about how that's done. You might know this already, but we'll kind of like review this. Everything, all matter in the world is composed of atoms. And when you combine atoms together, and well, if something's made of only one single atom, it's called an element. If it's made of two combined ones, then it would be a compound or a molecule. One single one is a molecule. If it's made up of molecules, it's a compound. So these are the list of all the elements in existence. Just comparing, like, lead. That's over here. That's Pb. That's lead. That is one atom. It's an atom. If the material is composed only of atoms of lead, it is an element. So these are the list of the elements, or list of the different kinds of atoms. Here's gold. And if you combine them over here, you can see that they form molecules. This is H2O, that's water, HCl. An interesting idea is that even if you combine, let's say, the barium to the chlorine, you're not going to eliminate the barium. The barium atom is still there. The barium chloride is certainly different from barium. Barium chloride is like a white powder. Barium is a metal. Chlorine is a green gas. But it might be very different, but the barium chloride still has the barium and still has the chlorine. So an elemental analysis of barium chloride will still catch the barium and the chlorine because they merged, but they did not lose their own identity as atoms. So the trace elements that we're going to be studying about the analysis of them comes from the atoms, the elements, not as they are molecules. The fact is, everything is impure, like paint, glass, metals. They've got some impurities. Nothing is absolutely perfect. I mean, maybe when you get to the semiconductors, the way they make them, it has to be absolutely pure, but we're talking about in things in the forensic world, everything is impure to a certain extent. But not everything is impure the same way. Some things are dirtier than others when they were manufactured. If we can find two pieces of evidence that are impure in just about the same way, they probably were part of the same whole in the beginning, and there is a connection between them. They probably had the same source. Now, here's an example. You have glass. Now, if glass is perfect, you're only going to find silicon dioxide and the soda and the lime. You're going to find the calcium oxide. You're going to find the silicon dioxide, obviously, and you're going to find the baking soda, the calcium carbonate, or whatever. Anyway, that's the pure glass, and you're not going to just have that because things get dirty and things can get into the glass making place, including like tiny pieces of metal. So glass has trace elements. You can find trace elements in glass, tiny amounts. No one can see them. They don't affect anything, but they're there. And if you have a sensitive enough instrument, you can actually identify the trace elements and how many there are in your glass sample. Now, if you have two pieces of glass that have the same trace elements in them, that's a sign that they were from the same batch, and there's a connection between them. And this is, of course, useful for evidence to trace, let's say, glass found on a suspect's property to glass found at the crime scene. Here's an application. It didn't really work that well, but it was an application of trace element analysis. This was done of a bullet. In the assassination of President Kennedy, a lot of people have a lot of different conspiracy theories about that, but we found the guy who actually shot the bullet. But there were two bullets shot. One killed him and one ended up somewhere else. So they say that, wait, it wasn't just one person, there were two people. So how do we know there weren't two people? Maybe it was somebody else. And, we can see how conspiracy theories come up with that they didn't really catch the real one. Anyway, so there was a claim that it wasn't the same assassin who shot both bullets. There was somebody else, and he wasn't caught. We still got to look for him, or whatever their theory ends up with. So what they did was they had both bullets, and they decided to do a trace analysis to see if they came from the same source. And it turns out that the trace elements found in the bullets both bullets were the same, implying they came from the same source. Now, it didn't really work because others tested their own bullets, and they found that, yeah, their own bullets was also, at least some of their own bullets were actually the same as those that shot President Kennedy. So this type of bullet matching is not really done much anymore. We do the striations to match the bullet to the gun that fired it. That is very useful. But the FBI is not doing this anymore. It might have some use, but the FBI does not trying to use that. They use other methods to try to match bullets. So how do you analyze an element? How do you know which element it is for these trace elements? Now, the rule is, now this is the fact, elements, atoms, if you put light into them, they will absorb light if it's the right frequency, the right wavelength. It absorbs light, and the electrons get elevated to a higher energy level. Let's take a look at a figure over here. The electrons of an atom are pretty much always in the ground state, and you excite them with some energy. Now we're going to talk about exciting them with light. You send light of a certain energy into these atoms. They will rise to a higher energy level, and they're going to fall back down once you take the light away. So the very common one is to fall right back to where it started. This is one form of emission of light from the atom. This is and they call it they call this an emission spectrum. A lot of different emissions would give you an emission spectrum. But anyway, you have the ground state. You send light into it. It'll absorb. Get into an excited state. It will drop down. Now, a very common one is dropping down all the way down to the beginning. However, it can drop down to other excited state levels, from here, let's say, to here. That'll give off a different energy. Now, this will be a lot of energy because it's going from this excited state all the way back down to the ground state. Here, it's going from this excited to a lower excited state. That's not so much of a light that'll be emitted. This will be light of a lower frequency or shorter wavelength. Here, it can also go down from here to here. That would be also of a higher energy, higher frequency than this, but a lower frequency than this. And it can also, once it gets down to this level, it can go down from there to the ground level. Eventually, it'll pretty much all get to the ground level, but once it gets from here to the ground level, this is again yet a third energy, a third wavelength of light that will be emitted based on only a single absorption over here. And you can think of some others. Maybe go from here all the way down to ground state. Again, there are many different emissions, but they are unique to each atom. And different atoms will have different energy levels and therefore different emissions. And once we excite it, in this case with light, we put light in there, it'll absorb the energy to this excited state level. We look at on our graph to see, this is one light of one energy level, another light of another energy level. These, let's say, 4 different energy levels. Okay, at these energies, only one element will produce this amount of light, this emission spectrum, these 4 lines of light emitted. Okay, that is how this is done. It produces what they call a line spectrum. It's not necessarily exactly a line. Back in the day, the things weren't all that precise. They really looked like lines. Now we see it actually does fade a little bit, but anyway, you can examine the line spectrum, the spectrum that comes out.